This diagram maps the current architecture of our solar system. The high-density, low-mass rocky planets cluster on the inside, while the low-density, high-mass gas giants occupy the outer orbits. This precise mathematical stratification suggests a specific set of physical rules govern the system's assembly. To find those rules, we have to look back 4.6 billion years. Before the Sun and its satellites existed, our local galactic neighborhood was a cold, dark stellar nursery known as a giant molecular cloud. This cloud was effectively a near vacuum. By mass, 98% of it consisted of primordial hydrogen and helium. The remaining 2% was a trace inventory of heavier elements, like iron and silicon, forged in the cores of earlier generations of stars. For millions of years, this diffuse mixture drifted in a state of equilibrium. The internal pressure of the gas perfectly balanced the weak inward pull of its own gravity, keeping the cloud stable and motionless. Turning this diffuse, disorganized gas into a structured planetary system required an intervention of extreme physical laws to force the cloud out of its stable baseline. Collapsing a stable molecular cloud requires an external kinetic catalyst to disrupt that million-year equilibrium. In our case, the shockwave from a nearby supernova, the explosive death of a massive star, provided that catalyst. The wavefront slammed into our local nebula, compressing the gas and dust. As the kinetic energy from the explosion plowed through the cloud, it bulldozed material together, creating localized spikes in density. These dense clumps eventually crossed a critical gravitational threshold. Their internal pull finally overpowered the outward gas pressure, triggering a continuous, runaway collapse toward a central point. The death of a neighboring star forced this chain reaction, ending the nebula's era of stability and initiating the formation of the Sun. Inside the collapsing clump, gravity aggressively pulled material toward a central focal point. Conservation of angular momentum governs this collapse, moment of inertia multiplied by angular velocity. Because total momentum remains constant, shrinking the cloud's radius accelerates its spin. This rotation generates outward centripetal force, flattening the spherical cloud into a protoplanetary disk. While the disk flattened, 99.8% of the total mass continued to funnel into the absolute center of the rotation. The immense pressure and friction generated as this mass crushed in on itself caused the temperature at the core to skyrocket. This superheated, glowing sphere of gas is known as a protostar, the infant version of our Sun. The flat, planar orbits we see today are the direct mathematical consequence of angular momentum resisting gravity 4.6 billion years ago. To find the planets, we have to look at the remaining 0.2% of the material swirling in the disk around the protostar. At this scale, gravity is too weak to work. Microscopic dust grains do not possess enough mass to attract each other through gravitational pull alone. Instead, friction within the spinning disk generates static electricity among the particles. These charges allow van der Waals forces to take over. When these microscopic grains collide, they electrostatically bond, snapping together into larger clumps. Van der Waals forces are weak electric attractions that hold neutral molecules together. Once these clumps reached the size of kilometer-wide planetesimals, their mass finally became high enough to generate independent gravitational wells, pulling in even more surrounding material. This atomic-level static electricity bridged the critical gap, holding the dust together long enough for gravity to become the dominant force of planetary construction. As planetesimals grew, they were shaped by an extreme temperature gradient radiating outward from the central protostar. This map shows the frost line, a critical thermal boundary located just past the orbit of Mars. Inside the frost line, intense heat vaporizes volatile compounds like water, ammonia, and methane. Only metals and silicates remain solid. Because these heavy materials made up only 2 radial distance from the protostar acts as a thermal filter, determining the composition and scale of every world in the disk. The accumulation of solid ice beyond the frost line triggered a phase of runaway growth. Jupiter and Saturn reached a mass threshold where their gravity became strong enough to actively sweep up the abundant hydrogen and helium gas directly from the nebula, swelling into gas giants. Further out, Uranus and Neptune captured a different mix of gas and heavy icy compounds, resulting in their classification as ice giants. This was a race against the clock. These worlds had to accumulate mass before the central star ignited and stripped the disk of its remaining gas. Roughly 50 million years after the initial collapse, the protostar reached its limit. The internal pressure at the core became so intense that it crossed the threshold required to sustain nuclear fusion. Hydrogen atoms began fusing together into helium, releasing an enormous surge of energy. The sun was officially ignited. Ignition created the solar wind, a powerful flow of charged particles radiating outward from the star. This wind acted as a cosmic sweeper, blowing all unaccreted gas and fine dust out into deep space. This event placed a hard cap on planetary growth, cutting off the supply of raw material and freezing the gas giants at their current masses. After the gas cleared, the solar system functioned as a chaotic, gravitationally unstable shooting gallery. Through a process called orbital migration, the gas giants shifted their paths, moving toward or away from the sun. Their massive gravitational fields acted like bowling balls, scattering the remaining planetesimals across the system. During this period, a Mars-sized planetesimal named Theia struck the early Earth. The resulting debris coalesced in orbit to form our Moon. These catastrophic collisions served as the standard mechanics of late-stage orbital stabilization. The material that was never absorbed into a planet remains today as the asteroid belt, the Kuiper belt, and the Oort cloud. Jupiter's gravity prevented a planet from forming between it and Mars, corralling those rocky leftovers into the asteroid belt. At the system's edge, icy remnants were gravitationally banished into the Kuiper belt and the distant Oort cloud. Over billions of years, the orbits locked in, and the catastrophic impacts slowed to a halt. The orderly planetary neighborhood we inhabit today is the stabilized output of a 4.6 billion-year equation of fluid dynamics and thermodynamics.